Hello and welcome to today's webinar. My name is Reid. I'm the Manufacturing Applications Manager here at GoEngineer. And today's webinar is being broadcast by a special guest of ours, Yuhao He from solidThinking. Yuhao joins us here at GoEngineer in Salt Lake City for the summer, kind of staying on site to help our technical team learn the ins and outs of the solidThinking line of products, in particular Inspire and Inspire Cast and ClickToCast. So you guys are in for a special treat today. You have an expert on this software. He's got some interesting content to go over. It is being broadcast live. That means you'll have the opportunity to ask questions as we go along. If you have a question at any point, go ahead and use the questions box in the GoToMeeting user interface, and we will address those at the end. So with that, Yuhao, take it away.
Yeah, thank you, Tyler. I'm Yuhao from Altair, and today I'm hosting this webinar about solidThinking with GoEngineer. Today's topic is about the effect of support assumptions on optimization results. Before we talk about the technical stuff, I would like to learn about your background with two simple surveys. If you can take a minute to complete the survey, that would be great. Okay, thank you. I see most of you are design engineer and mechanical engineers. That's great. That's the right user or audience for Inspire. And the other one is about optimization experience. Okay, that's great. I see the experience varies from Inspire tools and other tools, and some people doesn't have much experience about optimization. So I will make sure the discussion will be suitable for everybody. Now we can talk about the first is what is Inspire. Inspire is a concept generation or optimization tool that's designed for design engineers, product engineers, architects, and it empowers its users by creating structurally efficient concepts quickly and easily. As we may all know, in a product development cycle, the cost to fix a problem gets exponentially increasing when we approach the later stage of the design cycle. For example, it will cost $100 to identify a fixed problem if the problem was identified in the concept generation stage, versus it may cost $100,000 if the problem is identified and has to be fixed after the product has been sold. So in a traditional design approach, most of the problem will be identified and fixed in testing phase. That means there will be multiple detailed design, test failure, redesign, iterations before the product can be released. With Inspire, the idea is to help engineers to identify and fix problem earlier, especially in the concept generation phase. So there will be a lot of potential problems be identified and fixed in concept generation phase, so that there are fewer problems will be identified and fixed in the later stages. This way, the company can save development cost and save development time by using Inspire. Who is using Inspire? You can see there are a lot of companies from a pretty broad industry, from aerospace to automotive to heavy industry, architecture, etc. Some companies use Inspire because Inspire can help them develop efficient and lightweight structures. Other companies use Inspire because it can help them shorten the design, product development cycles and cost. Today we are going to mainly talk about three topics. What are support assumptions? How Inspire can help users take those into a consideration, and why proper assumptions are important. First, what are support assumptions? Here, I'm going to use this example to explain. In this example, there is a vertical I-beam and a horizontal I-beam. And I'm designing a bracket to connect those two parts. 5,000 Newton load is applied on the end of the horizontal I-beam. And there are 5,000 pretension load on each bolt. I would like to determine there are like 16 candidate positions for the ribs, and I would like to determine the best positions for 6 ribs. That means I would like to keep only 6 ribs, but achieve the maximum stiffness so that the loaded end of the I-beam will have the minimum deflection. So today I'm using topology optimization to answer a pretty classic engineering design problem instead of creating any organic or innovative structures here. So for the simplest setup, we could set up the optimization problem by fixing the 4 bolt holes attaching to the vertical I-beam, apply a remote load through a spider, and the load will be applied to the bolt holes that connecting to the horizontal I-beam. With this assumption, we actually assume all loads are transferred through bolt holes, and the vertical I-beam is very stiff, much stiffer than the bracket, so its compliance can be ignored. And the horizontal I-beam stiffness won't change the load path in the bracket. So what are we missing here by this assumption? First, we miss those 2 I-beams that have comparable stiffness as the bracket. Also, there is contact between the bracket and the I-beam, and also the pretension bolt. As we may know, the optimization results will be as good as our inputs and assumptions. And the stiffness and compliance from surrounding structure can affect the load path in the bracket and also the topology optimization result. If we oversimplify the problem, we could get a suboptimal design or solution. So how Inspire can help here? First, Inspire can model the assembly and optimize the structure within a complex assembly. Also, Inspire can simulate the contact with different level of complexity. I will explain about those later in more detail. And also, Inspire can model the pretension load, pretension bolt. Why proper assumptions are important, or what difference can we produce with different kind of assumptions? Here, I'm having 4 different levels of complexity to target this problem. That is, keep 6 ribs from the 16 candidates and produce the stiffest design. The first simplest setup is I only model the bracket, so there is no contact, no bolts at all. At the second level, I include the surrounding structure, meaning the other 2 I-beams, but I don't include contact or bolt pretension. On the third level, I add the contact, but the contact cannot separate, meaning like the green contact surface can only relatively slide to each other, but they cannot separate. And on the most comprehensive level, I allow the contact to separate and also model the both pretension. Here is the summary table of different setup and assumptions. First, as you can see, with different setups, the optimization gives me different designs. And with these 4 setups, the designs are all different. They all have 6 reps. To compare their performance, I use this full design space as a reference point, because no matter how I optimize the 6-rep design, it won't be as deep as this 16-rep bracket. I just use its performance as a reference point. And the displacement value is the displacement at the end of loaded I-beam, loaded ambient end. And here you can see, with the surrounding structure properly considered, the optimum design can uncover 35% more performance potential than the suboptimal design. I'm going to show you 2 setups in Inspire. One is the simplest setup, bracket only, and the other is the most comprehensive one. First, as you can see, Inspire can read all, most common CAD formats. Here is the model. First, I'm going to apply a remote load at the end of the I-beam, and I need to determine the center of this end. You can see it snap at the end, so it's very easy to determine the geometry. And now I'm applying the 5,000 downward load, 5,000 Newton in Z direction. And I'm touching this load to the both holes here. Okay, with the load setup, I can delete the I-beam because I'm not including them in the model. Then I use this fastener to identify single holes and have some grounded bolts created through the hole to fix those holes to the ground. Now I'm making the ribs as design space. This way I tell the solver and optimizer that it can remove material from the design space and leave a portion of the material that I ask. To make the design easier to interpret, I use this shape control, so the result will be more dense, will be denser, and easier to understand. I'm here using the extrusion control. That means I enforce the cross-section to be consistent along this direction, but the part not necessary to be made by extrusion. With this setup, the model is ready to run. we have the topology optimization, and the objective is to maximize stiffness. And I want to keep certain percentage of the volume within the design space. Mesh size, I want it to be 4 millimeters. And the run can start with this by clicking this run. And I have a model ready with the results, and we can look at that together. We can review the results by clicking the optimization button here. And you can see it indicates me 6 rates. Even though they are not full rates, but we can interpret them as full rates. Basically, it identifies the 6 most critical rates under this setup and show me a hint for the design. Then I'm going to show you the most comprehensive setup. Here, first we connect the parts with bolts first. You can see Inspire automatically identify those bolt holes, and I just need to click fasten and it creates bolts for me. Then I'm applying 5,000 Newton downward load. And fixing the 2 ends of the vertical I-beam as support. We have 5,000 Newton pretension load on the bolt. Here I can select all the fasteners and enable pretension with 5,000 Newton. The remaining work will be the same, make the ribs design space. And have the shape control to have sensor result. Inspire automatically identify the contact. If I click the contact button, you can see here the green surface is a regular contact and the blue surface is bounded contact. For the regular contact, when I submit the job, I have options. Either the contact is sliding only, which is simplified contact behavior, or I can ask the contact be able to separate if the load asks it to do so. This is a more physical behavior of the contact, but also takes more power to solve the problem. Yeah, again, with I have a model with the results ready. And I can review the results here. You can see the topology optimization identifies 6 ribs for me, but the locations are different than the previous setup. Now I can create the concept based on the topology results. And it's also very simple to set up. First, I make some design space and separate those bodies to individual parts. Delete the rib that's not indicated by the optimization, and only keep the necessary one. And I can boolean the ribs with the bracket together to make them one piece. And then create some fillets at the corner. Same thing for the lower ribs, and I'm not doing that here. You can see the both are deleted because I merged the parts together, putting the parts together. I just need to rebuild the bow. Just to click. It's starting all, everything's created. And apply the pretension to the boat again. And I can run the analyze with proper mesh density and context that can be separate. Here I have a model that imports all setups, all designs together, and we can compare their performance side by side. You can review the results here. And at the bottom corner, we have a compare result. And I can see their performance and their mass. The mass of the full design will be the same because I keep 6 ribs for each. And here you have the maximum displacement to compare. So several points I'd like to discuss with you before we ending this webinar. First, properly taking surrounding structure into optimization should produce more efficient concept. And adjacent structure has bigger influence on the optimization results as 2 scenarios. One, the surrounding structure stiffness is similar in the similar order of magnitude to the optimization target. For example, in our case, we have a vertical I-beam attached to the bracket. If I have a solid piece of block, then its stiffness is much higher than the bracket, then we probably can assume it's perfectly rigid. Another scenario is the surrounding structure stiffness is not uniform or homogeneous. For example, if we have a tube, imagine you cut a window on the tube, and if we design a structure that's close to the window attaching to the tube, then we probably want to take the tube into consideration because the tube stiffness is not uniform everywhere. And the last point is optimization with separable context that is the best design design, but it takes longer time to solve the problem. And I would suggest you to use this option only when the contacts are critical and play a big role in the load task. In our example here, you can see the last one. If I show you the deformation of it, the deformation here is scaled by a factor to more easily view. And you can see I wouldn't identify the importance of the lower true rate. If I don't have a separable contact, you can see that the design is not symmetrical up and down because we have a physical contact behavior in the optimization. And the lower rate works better under compression because the horizontal I-beam push the surface downward. And those two rates can only be identified when we have a physical contact behavior. Otherwise, if you look at other designs, the upside and downside rate distribution are the same, or it's symmetry about the horizontal plane. So that's it for today's webinar, and feel free to ask a question to the question box, and we can have like 5 to 10 minutes to answer your question.